Hello everyone! This is part 2 of how to use CFrames in Roblox Studio. If you haven't watched part 1, please go ahead and watch it before watching this video. The link is in the card and the description. In this part, we'll cover combining CFrames, translating along local and global axes like you see in these examples, and figuring out a world CFrame from a local CFrame and vice versa, which is common in game development. Before beginning, please don't forget to like, comment and subscribe to support the channel for more videos. Let's begin part 2. Towards the end of part 1, we were talking about combining two CFrames. I promised a more practical way of combining them. Intuitively, you may think that just add the two CFrames by using an addition. Let's see what happens when we do that. Let's create a local combination test variable, set to initial CFrame 1 plus initial CFrame 2 and see how it behaves. It didn't work, so the addition of two CFrames is not defined in Lua. It says vector3 expected got CFrame for the second argument. That means we can use a vector3 here. But using a vector3 won't give us what we want exactly. Let's try anyway, just to see what happens. Vector3.new, let's use 2, 2, 2. And let's use these two lines again to visualize the combination test. When I run, we can see that it works, but it only works for the position change. Because this is a vector3 variable, and vector3 can only store position information. So the position information has been increased and the new position is here. It is 3, 4, 5 instead of 1, 2, 3. The bottom line is, we can add vector3s to CFrames, but it is not the same thing as adding two CFrames together. So the question is, how can we combine two CFrames in a practical way? In order to combine two CFrames, the correct operation is multiplication. So let's come back here, comment these out, and instead of using addition, let's use multiplication. Multiply initial CFrame 1 by initial CFrame 2. Let's run this, and as you can see, it combined the two CFrames correctly. What if we had written it in the opposite order? Let's copy this again, paste it here, call it combination test 2, change its color to black. Now let's change the multiplication order. This time we'll have initial CFrame 2 multiplied by initial CFrame 1. Let's run. As you can see, the black one is at a different position than the first one, the brown one. So it is not the same thing. Multiplication order matters. So why could this be happening? For combining CFrames, we use multiplication, but it is not commutative. Meaning that CFrame 1 times CFrame 2 is not the same thing as CFrame 2 times CFrame 1. We have just seen that in Roblox Studio. Let's do an explanatory demonstration here. Let's assume that we have an arrow at the game world's origin and we would like to move it and rotate it. So we'll need to combine two CFrames in this scenario. If we first move, then rotate, it will move like that and then rotate. Since these multiplications are always performed in the local space, this would be the output. If we do it in the reverse order, rotate first and then move, it will rotate first like this and then move in its local axis. And the results are not the same. Their rotations look the same, but their positions are different. If we look at our example once more, the rotations of these two CFrames are the same, but their positions are different. The reason here is that the first one was moved and then rotated. The second one was first rotated and then moved. That's why we have two different outcomes here. So while combining CFrames, we should be mindful about the multiplication order. Alright, now let's talk about how we can translate CFrames along axes. Let's comment this out. I'll copy this line for the initial CFrame. And also I'll copy this in order to see its effects. If you remember, our initial CFrame is at 1, 2, 3 and looking at the origin. So I'm gonna create three different CFrames. Local final CFrame is equal to initial CFrame times, which means we are combining CFrames, CFrame.new, and I'll only pass in 1, 0, 0, which corresponds to the position information, 1 for the x-axis and 0 for the y and z axes. And let's call this final CFrame 1 because we are gonna create two more. Let's rename as 2 and 3 and let's change their values as 1 in y and 1 in z axes. So these are the final C-frames, and this time I'm gonna use the animated axes arrow method of the visualization. So visualization.animatedAxes arrow. This will take in two C-frames, the initial and the final. It will perform an animation from the first C-frame to the second C-frame. We can give a color. Let's use white. I'll copy this and paste. Adjust for final C-frame 2 and final C-frame 3. Let's adjust our view and click Run. It started at the same place, then diverged into three different directions. Let's stop and add a through here so it visualizes the initial C-frame as well. As you can see, they all moved by one stud in X, Y, and Z directions. The rotations and translations are all in local axes as we have discussed. But sometimes we may want to do these translations along the global axes. It is very simple to do that. We just need to make sure that we move the object before rotating it. Let me explain. Here we first move and rotate, and then move by one stud in the x-axis. This movement is in the local x-axis since we rotated the object before moving it. If we move the object before rotating it, it will be like moving in the global axis since initially the local axes coincide with the global axes. Let me show you. Let's comment these out and paste here again. This time, I'll change the order of multiplication. I'll save and run again. You can see that the translations are in the global axes, not local. So this is how we can change the axes from local to global while translating C-frames. Let's have an example for rotation as well. Let's get rid of these again and paste here. Let's assume we are going to rotate this. Local final C-frame will be initial C-frame combined with CFrame.angles, and I'll use mat.rad4500. Let's use this method here again to animate. If I run, it is rotated along its local x-axis. This is the axis of rotation. This is how we can rotate along local axes. If we want to rotate along global axes instead, it is very similar to our previous example. We'll change the order of multiplication. When we run it, we can see that it is rotated along the global x-axis from the origin of the game world. Sometimes we may want to rotate it from the origin of the object itself, but along the global x, y, or z axes. Let me explain how we can do that. Here, we are actually rotating around the origin and then combining with this C-frame. The initial C-frame has both rotation and position information. But what we should do is to complete all the rotation first and then add the position information. So here, instead of initial C-frame that has both rotation and position information, I'm gonna use its rotation only by typing .rotation. This time, we'll only be combining the rotations of the initial C-frame and the CFrame.angles. After that, if we want to end up at the same place, we should add the position value as well. For vector 3 values, we could use addition to combine if you remember. So we'll add initial CFrame.position, which is a vector 3. If we write it like that, with separated rotation and position values, it will be rotated along the global x-axis, but from the origin of the object. So this is the axis of rotation, but the origin of rotation is the model's origin. This is how we can rotate objects using C-frames around the global axes from the global origin and also around the global axes but from their local origins. Next, I'm gonna show you how to handle two scenarios that are common in game development. But to understand them better, let's take a look at the logic behind combining C-frames a little closer first. Let's assume that this is the global origin. And we have a representation of C-frame here, which has a position from the origin and a rotation. Let's call it CF1. And we have another C-frame. It also has a position from the origin and a rotation. Let's call it CF2. We know that we can combine C-frames. We can call the C-frame from CF1 to CF2, CF1 to 2. By definition, CF2 is the combination of CF1 and CF1 to 2. And as you can see, CF1 and CF2 are calculated from the origin. So these are world space values. But CF1 to 2 is calculated from CF1 to CF2. So it is in the local space of CF1. Usually we have two cases in game development. The first one is we know CF1 and we know CF2 and we would like to find CF1 to 2. Let's assume CF1 is our character's CFrame value in a game, and CF2 is our opponent's character. We know their position and orientation with respect to the world space, but we may want to see how we can manipulate our gun to point to CF2, which is the opponent's position, like shooting an arrow. In this scenario, it would be a good idea to find CF1 to 2. The second common scenario is that we know CF1, so we know our character's position, and we know the opponent's position with respect to our character. For example, it is like in front of us and 10 stats away. So we know the CF2's position with respect to our character's position, which means in the local space of CF1. But we want to know the world space values of CF2. If we were to send an object to the opponent's position, we would need to calculate the world space position of CF2 based on these two CFrames. Another example can be a rocket launcher target activated from our base. These are two very common problems that we come across in game development, so it is important to know how to tackle them. The second one is quite straightforward with the given formula. So CF2 is CF1 times CF1 to 2. It is easy to find. But the first one is a little harder. We need to know a few other things to handle that. Let's start with some properties. The first one is the identity property, and it is defined for any operation. If A is operated by the identity, the result will not change. It will stay as A. Let's see some examples. For addition, it is A plus I is equal to A. For multiplication, A times I is equal to A. So we know that for addition it is 0 and for multiplication it is 1. Also, we need to know about another property called the inverse property. By definition, it is A operated by the inverse of A is equal to I, identity. Let's see examples again. For addition, A plus A inverse is equal to 0 because the identity for addition is 0. And for multiplication, A multiplied by the inverse of A should be 1 because the identity for multiplication is 1. We know that for addition, the inverse of A is negative A, and for multiplication, A inverse is 1 over A. Let's switch our focus back to CFrames now. For CFrames, the identity property can be achieved by using CFrame.identity. It is also created when we use no arguments for the CFrame.new. We saw earlier that it created an array of numbers like this: 0, 0, 0 for the position, and 1, 0, 0, 0, 1, 0, and 0, 0, 1 for the rotation, which means unit vector in x, y, and z directions. And if we look at the inverse property for the CFrame, it is not straightforward like for the addition or multiplication. But luckily, we have a method that gives us the inverse of a CFrame, which is CFrame::inverse. We can use this in our calculations. Let's go back to Roblox Studio to have an example on the inverse. Let's comment these out, copy and paste. Let's get these as well to print and visualize. I'm gonna create another one, initial CFrame2, and this time I'm gonna use the information from the initial CFrame and I'm gonna take the inverse of that. Let's use some colors to distinguish these two. Yellow for this, and for this one, let's use purple. Let's also create a combination of these two. Copy and paste, rename as final CFrame. This is gonna be initial CFrame times initial CFrame2. Let's change the color to orange. Let's run. This one corresponds to the initial CFrame. As you can see, it is at 1, 2, 3. And we have this one here. It is at 0, 0, negative 3.74 and has some rotation values. And this is the calculated inverse. As you can see, at the center, we have the final CFrame, which is the combination of initial CFrame and initial CFrame2. And since initial CFrame2 is the inverse of initial CFrame, when we multiply it, as expected, it will return the identity value, which is 0, 0, 0, and the rotations are the same as the global axes. If we look at the values for the final CFrame, these three position values are very close to 0. We have values close to 1 or exactly 1, and the rest is close to 0, so they can be considered as 0. So the values look as expected if we ignore some rounding errors in the calculations. This was an example for the inverse property. Now let's see how we can use this to calculate what we were looking for. So we know the values of CF1 and CF2, but we want to find CF1 to 2. We can multiply both sides of the formula with CF1 inverse. So we can get the inverse with the inverse method and multiply both sides. If you remember, CF1 inverse combined with CF1 will result in CFrame.identity. And we know that if we multiply a CFrame by CFrame identity, by definition, it will give us the same thing, CF1 to 2. And this is how we can find CF1 to 2. It is CF1 inverse times CF2. You may find this hard to remember or hard to calculate every time, but Roblox makes our job easy. We have some methods that we can use instead of this formula. CF1 to 2 is CF1 colon to object space CF2. So we are getting the word coordinate CF2 and convert it to the object space of CF1, which corresponds to CF1 to 2. And although the second calculation is quite straightforward, we have a similar method for that as well. CF2 is equal to CF1 colon to word space CF1 to 2. This time we get the combination of CF1 and CF1 to 2, and the result will be CF2 from the word origin. Let's use these in our example as well. I'm gonna comment these out, copy this portion, change the name of the CFrame to CF1, similar to how we have discussed. Let's create another one, CF2. I'm gonna change the position values of it as 5, 4, 3, and it will face towards the origin again. Let's use a different color, like purple. So these are CF1 and CF2, and let's create local CF1 underscore 2, CFrame 1 to 2. And as we have discussed, it will be CF1 colon to object space CF2. If we combine CF1 and CF1 underscore 2, it will give us CF2. Let's create a local combination is equal to CF1 times CF1 to 2. Let's copy the animation code from CF1 to combination to see how it works. Let's run. This is CF1 and CF2, and the animation goes from CF1 to CF2. Let's do an example for the other scenario as well. We are gonna use CF1 again, but this time, instead of this, we know the CF1 to 2, and it is going to be CFrame.new. Let's put in a position here, 0, 1, 0. These will be in the local coordinates of CF1. So when we say 1 here, it means 1 stud in CF1's local positive y-axis. I'll also add some rotation. Let's do CFrame.angles, and I'll use math.red 90, 0, 0. Again, these values are in the local space of CF1. It will rotate along the local x-axis of CF1. Let's calculate CF2 based on these two by using the toward space method. CF1 colon toward space CF1 underscore 2. This will give us CF2. And I'd like the animation to start from the origin. We can use CFrame.new for that. And the animation's destination will be CF2. Let's get rid of this last argument so that the initial CFrame isn't visualized at the origin. Let's run it. As you can see, we calculated CF2 based on CF1. We added 1 in the local y-axis of CF1, and the rotation is along the local x-axis of CF1. Let me show you again. So this covers everything important about CFrames and how we can use them confidently in Roblox Studio. I hope you enjoyed the video and found it helpful. Please like and subscribe to support the channel for more videos. If you want a new game development tutorial, let me know in the comments. You can get access to the Roblox project file from Patreon. The link is in the description. Thanks for watching, and I'll see you in the next video.